All right, everybody, welcome back. Let's now talk about how you actually use Newton's laws in practice, how we can use them to solve different types of problems. So first of all, let's remember the laws. An object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity unless acted on by an unbalanced force. That's the so-called law of inertia. The second law is the mathematical one. That is the one we're going to be spending most of our time talking about for the next few minutes. F equals m times a. An unbalanced force causes an acceleration to happen. And finally, the third law, for every action, there is always a pose and equal reaction. Now, how do we use these? Well, we do spend most of our time talking about the second law. We do focus most of our attention on the second law. Let's take a look at how we use it. It is probably easiest and certainly the best approach to take every problem and draw it out. We use so-called force diagrams or free body diagrams, sometimes called FBDs. These identify all the forces acting on the body and in their correct directions. That is extremely important. The body typically is replaced by a dot or a box. For example, I've got my little knight statue right here. If you look, there are at least two forces acting on it. The knight's weight acts down, and the reaction force, third law force, sometimes called the normal force because it is normal to the surface, meaning perpendicular, that acts up. And those two forces are equal but opposite. And of course, the knight is not moving. Now, there also very likely is friction all around it, but since those friction forces are balanced, they don't really do a whole lot here. However, it of course can get messy, especially when there is motion involved, primarily acceleration. Now, the best way to think about Newton's second law is this way. Not just F equals ma, but the sum of the forces equals ma. Sigma means the sum of. Vectorially, the sum of. The forces equals mass times acceleration. So how do we use this? Well, it does get a little complicated. So we usually, especially if we're in two dimensions, we have to treat the forces along their particular axis separate from each other. In other words, if you have forces in the x direction, you got to keep them separate from the forces in the y direction. It is very similar to the philosophy behind solving projectile motion problems. That is to say, if you remember in projectile motion, we had acceleration in the horizontal direction, which was usually 0, and we had acceleration in the y direction, which was always g. Pretty similar thing going on here. So this is a classic problem. It's known as a dynamics track or an air track sometimes. And you have one car that's being pulled by a hanging weight. So there is a car. This is actually, this was demonstrated in the last video that I posted, by the way. So you happen to have one car on wheels so that the friction is pretty low. The car on wheels is represented by M1. The weight hanging is M2. So let's do free body diagrams for each of these guys. So for the one on the left, for M1, there is its weight pushing down on the track, and there's the track force pushing back up, and those two things are equal. The normal force is pushing up, and the weight 1 is pushing down. And as far as the car is concerned, it's a string with tension in it pulling to the right. Now, for the hanging weight, M2, it's got its own weight being pulled down, W2, and it has tension pulling back up on it, which we assume is the same as the tension that is pulling on the car. We assume it's exactly the same. And that is, of course, one of the big assumptions when we solve problems like this, that the tension is constant. It may not always be. There are instances where it's not, but for the simplest problems, it is definitely equal, or at least very close to being equal. So now that we've identified the forces, we can use the sum of the forces equals m times a, and we can solve in each relevant orientation. For example, for the first body, the motivating force is T. That's pulling it to the right, and that equals its mass, m1 times a. We also know that the normal force and the weight 1 are equal to each other, so that's great, but we don't need it. Now, in the force that's hanging, the weight that's hanging, W2 pulls it down. That's the same direction, relatively speaking, as the car is moving above. That is, the car is moving to the right and the weight is moving down. That's all the same basic clockwise direction if you think about it. Weight's pulling down, tension's holding it back. Weight 2 minus tension equals M2 times A. That's still F equals ma. It's the sum of the forces because there's two forces acting on it. That equals m2 times a. Note, by the way, that there's no friction with the hanging weight because it's not in contact with anything. Notice also that I don't have friction with the car, but if there was friction, it would act horizontally opposite the tension pulling to the right. Also note that I have consistent use of positive sign convention for the acceleration. Now, if you solve that, you can add the two equations together, do a little bit of algebra. T equals m1a and w2 minus t equals m2a. All I did was plug the first equation into the second one, do a little bit of algebra, and we end up with this solution that the acceleration of the system is equal to m2g divided by m1 plus m2. So it's a little messy at times, but that's how you solve these problems. Now, if there had been friction, it would be between M1 and the track, and we could indicate it as little f. In fact, speaking of friction, well, it would look like that, T minus little f equals M1A. Now, what exactly is friction? Well, friction is an electrostatic force of attraction between two bodies that generally are in contact with each other. There are ways to quantify it. Usually we just measure it. Let's see how we put this into action in another problem. We have a toy car here, the mass of 0.8 kilograms. It's got a motor providing a thrusting force of 3 newtons, but there's 0.5 newtons of friction with the ground. So what's the acceleration of the car? We're going to do our free body diagram. Get the thrust force to the right, friction to the left. The weight is down and the normal force or the reaction force is up, equal and oppositely directed to the weight. Sum of the forces equals m times a. That's the thrust force minus friction equals ma. That's 3 minus 0.5 equals 0.8 times a. And you solve that bad boy, you got 3.1 meters per second squared. Think you got it? Well, what if we apply forces at angles? It can get a little bit messy. For example, we've got this person pushing a shopping cart. Let's say they're exerting a 10 Newton force on this cart that's 2.4 kilograms, but they exert it at an angle of 20 degrees to the horizontal. How do we find the acceleration? Well, we have to use the horizontal component of the force. The horizontal component of the force is 10 times the cosine of 20. There's still a weight down and a reaction force up. And if there's any friction, it's going to be to the left. So that when we solve this problem, we've got F equals ma. That's 10 cos 20 equals 2.4a. Therefore, the acceleration is 3.9 meters per second squared. I do need to remind you, make sure your calculators are in degrees mode when you are solving problems like this. Okay, as I said, problems can get a little bit tricky. For example, let's take a look at what happens when you're on an inclined plane. If you're on an inclined plane, it's almost as though you have a coordinate system that has been rotated by, in this case, theta degrees. Well, it's not that bad if we kind of play along with the rules of sine and cosine. In this case, if we use similar triangles, we can actually see that part of the object's weight can be thought of as pulling it down the plane, and part of the object's weight can be thought of as holding it onto the plane. So with the similar triangles argument, we can find out that the so-called parallel component of weight that pulls it down the plane is equal to mg, its weight, times the sine of theta. And the component that holds it onto the plane is mg times the cosine of theta. So this is something you don't want to have to reason through every time you see a problem. If you have a problem set up such that you know the angle with respect to horizontal is theta, then you can say with certainty that the parallel weight pulling it down the plane is mg sine theta, and the component holding it on is mg cos theta. And if, of course, you have friction, that acts opposite the direction of motion. Now, the last type of problem that I expect you will see in this chapter are so-called statics problems. That is, problems where things are not in motion instead of being accelerated. For example, let's say that we have a street light, a stoplight that's hanging. It's hanging from a single cable, and the stoplight is 40 pounds, then there's 40 pounds of tension in the cable. Now, if it's hanging from two equal cables, then there's 20 pounds of tension in each cable. Not really too surprising there. On the other hand, what happens if there's some non-zero angle between the cables? Then it gets messy. Then what we actually need to do is break those cables into components. So I am going to assume for this first example that they're of equal length, which means that each cable is going to have tension T in it. Now, if that's the case, I can imagine that there's a horizontal component of tension for the left cable and a vertical component of tension for the left cable. And of course, it's a mirror image on the right side, vertical component of tension for the right cable and horizontal component of tension for the right cable. And of course, these two guys should be equal. That is, the ups should be equal and the lefts and rights should be equal, but oppositely directed. So breaking this down, we can see with a typical argument for breaking vectors into their components that I have called, this is 40, which is half of 80. So this component is t cos 40, and the horizontal component is t sine 40. It's the same on the left as it is on the right. Notice, by the way, that how I define the angle makes the problem easier to solve. If you had defined the angle with respect to horizontal, the only difference would be the sine and cosine values would be flipped. And of course, the 40 pounds still acts on the stoplight pulling down. So as far as the stoplight's concerned, it's got two cables pulling up on it and its own weight pulling down on it. So we can solve this actually without too much difficulty. The problem is, of course, that the tensions aren't in the same direction as the weight. That's why we broke them into their components. So for the so-called ups, I've got t cosine 40, that's for the left cable, that's the component that goes up, and t cosine 40 for the right cable component that goes up. That's ups, and the down is 40 pounds. Now, the left component is t sine 40, and the right component is t sine 40. They're equal to each other, which, is great, but not terribly helpful in this problem. So when we solve this, we got 2t cosine 40 equals 40, and solving that, we get 26 pounds in each cable. You'll notice, by the way, if you add 26 and 26, you do end up with more than 40, and that does make sense. In fact, the greater you make the angle between them, the higher the tension goes. In fact, you can't possibly make the angle 180 degrees because the tension will, believe it or not, approach infinity. That is to say, it's not possible to have something hanging from two cables without there being at least some angle. Now let's say, for example, that the cables were not of equal length. Is the problem tougher? It's a little bit trickier. If they're not of equal length, the tensions won't be equal, but the approach is exactly the same. You're going to have left and right components. They are calculated the same way, but you end up having two equations with two unknowns. This is a fairly typical type of statics problem that you may see. I have noticed that this one is in the notes packet. So there you are. That's what's going on in this chapter. Please reach out if you have any issues or if I can help with anything as always. Take care.